Yes, good morning. Today we will discuss the two independent sample t-test. So let me just write that as a title here. Two independent sample t-test. Two independent like that. Sorry for this. I am not yet savvy on using the independent sample like that. Sorry for that. T-test. So there are two samples that you are testing. T-test in your the t-test tests whether the means of the samples are statistically equal or not. So it's a simple it's a test of quality of means. Two independent sample t-tests. There are at least three t-tests rather. One sample t-test, the two paired t-test, the two sample paired t-test, and this one. So we're focusing on this one. There are two samples and then t-test, two independent sample t-test. And so it's a very simple test. It has a measure of the separate, it comes up with a measure of the difference of means, and that difference has a statistical distribution, and when it has when a difference in means has a statistical distribution, then if it's rare or if it's common to arrive at your measure, at your t value, right? The difference in mean. If it's rare, or if it's rare to arrive at a higher t than your t, then you should accept your results as valid. That your results, that your means are not equal. Usually, you're comparing means that are not equal in the first place, right? Well, you're trying to test them statistically, right? To test the inequality statistically. So what is that measure actually? You just there's a t, the t value. What do you call the t value? It's just it's a ratio of the difference in means over the standard error, right? How is that so? Conceptually, let's say here is two sets of experiments. One, two. This is the number line of the results of the experiment. So this is 0 to infinity. And one set, let's say there are 5 observations, for example. So let's say the red one. The red observations are here. Well, this is by chance. So they're all over. Well, it spans the number line that I just drew. That's the observations of your first sample. Yeah. This is the number line. And then you have your second sample. You have also the observation. Maybe here. 1, 2, 3, 4, 5. Yeah. So if you have such a result of your two samples, the observations are laid down over there. By observing them, you can say that they're mixed up, right? One is just mixed up with the other. You can't distinguish one group from the other. Yeah, or by just observing the results or the measurements, you can just yeah, intuitively you can say that one group is different from the other. But if you have another experiment, which you have another experiment like this, and where the results are really separate, like distinct. One, there are observations for the red sample is here. The observations and the green samples are here. Then you could immediately say that this group are quite different, right? They have different means and they're quite separate from each other. But here, the means might, in the first experiment, the means might be different, but the individual observations are actually very mixed up. For example, let's say the mean of the red group is just right in the middle. Well, I'm just guessing, I suppose for him, because this is the middle of the range, more or less the middle of the range of observation. So the mean, more or less, that's where the mean is located for the red group. And for the green group, it's almost the same. That's also here. That's a mean of the observations of the green group. Here, in the second experiment, the mean of the red group would be in the middle. Well, sorry for that. I can, yeah, and the mean is there. And for the green group, the mean could be here, right? So what can you can see from this illustration that the means are far apart. They have a very large mean difference than the first experiment. Very small mean difference, right? Like this mean difference, very small, and this is very large. So if you're comparing when comparing group separateness, like this green and separate from these, normally intuitively compare their means, but that's not enough. You should also compare how the individual observations of the groups are separated from each other, right? Or one group is separate from the other. I'm talking of the variance of one group, the variance of the other from the mean, right? For example, in the first set of experiment, we have like the variance is big, right? Here. Sorry. The range, at least for the range, we're not, you can more or less intuitively see the variance by looking at the range, right? The variance, the numbers, the range of numbers are so varied. So you have a large variance, right? From that to that, from the smallest to the highest number. And for the green group is from here to here. So the variance is quite large as well, right? I mean, here in the second set experiment, the variance of the red group is from here to here. So it's quite small, smaller than the first experiment. And from the green group is like that. So the variance is quite small, right? The variance is quite small. So if you can see, not all, and here the members mixing up with each other, the red group, you can see that the means are not only the means are very close to each other, but the variances of their are very wide. They're actually overlapping each other. The variances of each group, the variance, overlapping. But here you can see that the mean difference is quite wide, and the variance of each group is quite short, or quite short. So intuitively we can differentiate it by But look at their variance, right? Look at the means and their variance, the variance of the groups and their mean, the mean difference in the variance. You can have a measure of how separate they are. One might say that this is one just one group. This first experiment is just one population or one group, one population, one population. It came from one population because they are mixing up, and these are separate populations. Because separate the second separate, yeah, separate populations or different populations, different means. But here you can say just one because they're mixing up. The members are mixing up together. And here they're quite separate from each other. Means are quite separate. So an intuitive measure could be the a measure of how separate groups are would be the ratio of the mean differences and a measure of the variances. Called the standard error. All right. It's related to the variance. Yeah, right. Standard error. So how is that done? Well, you can operationalize by really computing for mean differences and the standard error and get the ratio. And that's the t. That's the t value. So that's how it's done. So let's go to phase 2. So we have the t, which is a measure of the how different are the means. So, well, it's just the, as I said, the ratio of the means of one group. This is the t. The standard error is computed at like this for samples that have equal number of members, equal number of objects, equal number of observations, n being n1 plus n2. I mean, the members of n1 plus the total, and the total number of observations of group 1 and group 2 plus n. This is the numerator here is the standard error. So, so as I said, it just measures, mean differences. It is large, and divided by the standard error. Standard is just a standard deviation over the square root of n. So t measures how many times mean differences is greater than the standard error. Yeah, so if it's very big, then chances are the means are very separate, and your standard error is very small. Well, if there's since this is just a division, this the numerator is a big one and this is small one, you have a big number. What if you have a standard error that's big and you have a small mean difference? I mean, they're very close to each other. The means are very close, so you have a very small t, or which means a very small t. Chances are the differences are not significant. It also means that your observations are quite intermingling with one another. They're overlapping with one another because of the very large standard error, right? I mean, it means you can distinguish groups by just observing the data, right? Because some members of group 1 are within the range of group 1. There are also members of group 2, and within the range of group 2, there are also members of group 1. So they are what you call, I just call it quote unquote overlapping members of group 1 and group 2. That's the case of the page that I saw here. Here, then the first experiment, there are actually all the range of let's say for the red group, the range of observations quite include a lot of observations of the green group as well. So here in the first group, and also with the green group, the range of the green group quite include a lot of remaining uh, red group. So that's what I mean by uh, the standard error is quite very big. And if you have a very big standard error here, then chances are their t is very small, right? And would be smaller if you have a big number here. Of course, you should look at the mean difference first. If you have a big mean difference and have a small standard error, then chances are your groups are separate. But you have a small mean difference and a big one, the chances are your groups are not separate. Right? So you have the t, and it has a distribution, the t distribution. You can look it up. So we're given your t, or you know the probability of anything less or anything of any t less or more than your t, right? Since it's a probability distribution, right? You have a t distribution like this, so maybe like that. So if you have a t, you have a t here, your computed t, then you know, since it's a distribution, you know that anything less than your t or anything more than your t, you know those distributions because it's just the cumulative. Yeah, is this shaded areas is just 1 equal to 1. So if you have your t here, you know your probability of t anything less than your t, because anything more than your, these are just complements, right? If this is 0.05, then that is 0.95, or if that is whatever number that you get, and the other side would be the complement, all sums to 1. So that's it. And then you compare your t with the known. Since the probabilities are known distributions and they're already tables, right? Or you can, yeah, the software can just compute it for you. It's probability of your t, probability of t greater than your t, or the complement of it is t less than your t. Yeah, usually it gives the probability of t greater than your t. So if you have a t like I don't know, like 2, whatever, 2.5 here, then it gives you the probability here it might be less than. Usually it's less than. Not sure. It could be less than 0.05. Usually with large t, usually like that. So 0.05 is probability, but it really depends uh, on on your t carb. There are many t carbs depending on the degrees of freedom. Yeah, right. Degrees of freedom. Degrees of freedom. So that's how it's done. The t-test. So hypothesis testing. It's easy because you have a known distribution. Mm-hmm. Mm-hmm. That's the t-test. Let's illustrate this with a I'm screen sharing, so I can open my page, for example, to get the t-table, for example. Oh, what's this? Some music from my wife. T-test. T-table, t-distribution table. All right, I have a PDF file here. I don't know. All right, I need that. So we have a t distribution. Yeah, it gives a probability of a t anything higher than your t. This is the one that we need. So your degrees of freedom, which is just with 2 sample tests, it's just the number of observations minus 2, right? Because and minus 1, because yeah, it's degrees of freedom is for two samples. It's a number of The degrees of freedom is number of samples or number of observations minus 2. Let's say you have 20 observations minus 2 here. And if you choose your significance level at 0.05, these are, so 18, that's a 1.734. That's a critical T. So a T of 1.734 gives a probability of 0.05 of anything higher than 1.74. Yeah, understand that? So let's just see. We have 20 and then we have 1.734, right? Let's say. So so a T of, in my case, if there are 20 observations and degrees of freedom is 18 df, and the critical T for a significant level of 0.05 is 1.73. I don't know what it is, something like that, 1.7. So that's 1.734. Yeah, 1.734. So that's your T, the critical T that gives you a probability of 0.05 to the left of 1.74. What does that mean in plain English? Well, it means that the probability of getting anything or any T, any T higher than 1.74 is less than 0.05. And if you have you set your standard to be 0.05, you set your significance level, meaning your risk-taking attitude of accepting or rejecting the results is 0.05. Anything more than that, you won't really accept your results. Anything less than that, you accept your results of unequal means. So if you get, for example, 2, as a man of 2, you know that the probability of getting a 2 is less than 0.05. It's rare to get a higher mean difference than your mean differences. It's rare, right? It's rare because it's less than 0.05. So you reject the null hypothesis of equal means. How it means. So voila. That's it. That's how you test, how you get your null hypothesis. How you test your null hypothesis. Remember, the null hypothesis, by the way, is that x1 is equal to x2, right? The means are equal. That's a hypothesis. And in the books, they call it the rejection region. But I want you to understand what are you trying to say when you reject. When you reject your null hypothesis, it means you're accepting your results are that the means not being equal, right? Why? Because when you compute your T, let's say your T is 2 and the critical level is 1.734, you have 20 and 18 degrees of 20 total observations. You have 18 degrees of freedom. So you get a 2, and 2, you know that somewhere here lies to the right of 1.735. This is the number line. This is the number line from 0 to infinity, right? So 2 must be to the right of 1.035, and it gives you a probability less than 0.05. So you are actually with that very rare chance that a higher P or higher mean difference will occur in another experiment that's very rare, then you are actually you're actually seeing that or proving or seeing that your mean differences are quite significant, right? Because it's rare to have a higher mean difference. than your own mean difference that you got from your experiment. Rare meaning it's less than 0.05. That's what it means. Thank you.